Hello, this is Dr. Christy Patton-Lukes, your professor for Chemical Engineering 5220. This is the wrap-up for our lecture in class on mixture properties. And just very quickly, we had been defining that the specific M, where M is any of our energy functions, is the sum of the x sub i's times the partial molar quantities for each of those substances I, and that the partial molar quantity is defined as how the extensive version of M changes with respect to the number of moles of species I when I don't change temperature, pressure, or the number of moles of the other species. And we could also define a delta M of mixing or an excess property as shown here. Just all variations on these energy properties or volume or entropy. And we had done an example where we derive partial molar C sub P. So C sub P is dH dt, and partial molar C sub P is how the partial molar H changes with T, holding again P in composition constant. And the point here being that the interrelationship between these various notations does seem to kind of carry through to other variations on them that maybe you might not have expected. So, for instance, C sub P is a derivative of an energy function. And then we looked at the generic M again for binary mixtures. And if we looked at that case, then we just have x1 partial molar M1 plus x2 partial molar M2. But if x2 is 1 minus x1, then we have dx2 is negative dx1. And I can make some substitutions, take some derivatives, and I ended up showing that the partial molar property 1 is the specific property M plus x2 times how the dm changes with x1. And for m2, I get m minus x1 dm dx1. Really, that sign change there is because dx2 is negative dx1. And we were just about to start this example here, where we have some actual data for delta H of mixing. And A and B are temperature dependent, and what we were asked to find here is the difference between the partial molar and pure component heat capacities for these species, and look specifically when x1 is 0.5 and T is 300 Kelvin. Now, the most important thing to recognize is that I can do algebra, I can even do basic calculus with these functions and still have the rules apply. So, for instance, C sub P is a derivative. It is a derivative of H. So we have C sub P is dH dt at constant P and X, and partial molar C sub P is dH partial molar dt P and X. Since they're both the same type of derivative with the same path, I could combine those. So the excess property for C sub P is d dt of partial molar H minus pure H for species I. And that would all be, of course, at constant pressure and composition. So what we need is expressions for this HI over bar minus HI under bar, okay? And we've seen earlier that this is just really delta H of mixing, a partial molar delta H of mixing. So I've written in the paths and then written this out explicitly. Now what we had just defined was formulas for partial molar property. So for species 1 property M, partial molar M is equal to the M plus x2 times dm dx1. So if I wrote that out, here's my H well, this is really H1 excess, is delta H of mixing for the mixture plus X2 times the change in delta H of mixing for the mixture with respect to X1. And for species 2, so H2 excess, and I shouldn't be putting over bars on that, sorry about that, is delta H of mixing minus X1 times that derivative. So what I want to do now is write out the expression for delta H of mixing in terms of just variable X1, not X1 and X2. So X2 is 1 minus X1, and then this is times A plus B, and then X1 minus parenthesis 1 minus X1 is the same as 2X1 minus 1. And if I multiply it out, you don't have to, but the math is easier if you take the time to do the algebra now. Then this is going to be X1 times A minus B plus X1 squared times 3B minus A minus 2B X1 cubed. And I can take the derivative of this with respect to the variable X1. So that's just going to be A minus B plus 2 times X1, 3B minus A minus 6B X1 squared. So now I have all the pieces that I need to substitute in. I am, well, I'm not going to do the rest of the problem for you. I want you to work through this on your own. But this is going to give me the H1 excess, which will allow me to then take the derivative with respect to temperature of that expression. All right, so I'll have it in terms of x, and I can evaluate it for when x is equal to 0.5 is what they specify there. You should end up with H1 excess and H2 excess defined as functions of a and b when x1 equals 0.5. Then I end up with these expressions. And then I'm just going to take the derivative of that with respect to temperature. Now these are both simple functions of temperature, so I will end up with, when you take that derivative, the 1/4 is a constant as far as temperature is concerned, so 1/4 of the derivative of A with respect to temperature plus dB with respect to temperature. And when you plug numbers in, try this, make sure, but 4.344 joules per mole Kelvin is what I got, and for species 2, it is 21.4 joules per mole Kelvin. So check that out. That should help you with your homework. See you in class.